Hi students, welcome back to our subject engineering materials. Yes, in our subject we have seen about the phase diagrams, ferrous and non-ferrous metals, properties of materials, testing of materials in the previous 4 units. In unit number 5 we have seen about the advanced materials and tools. In this we have already seen about the smart materials, ferroelectricity, piezoelectric and optoelectric properties, semiconducting behavior of laser and optical fibers, photoconductivity and superconductivity, the nanomaterial synthesis properties and application, and biomaterials in the previous lecture. In this lecture we are going to see about the superalloys and shape memory alloys, material characterization technique, scanning electron microscopy, transmission electron microscopy, and atomic force microscopy. As a current beyond syllabus 2 in our subject, we are going to see about the less weight high strength material as a carbon fiber material with its property and its application. Now we will going into the topics. First one, the superalloys. It is a group of nickel, iron nickel and cobalt alloy used in jet engines. These metals have excellent heat resistance properties and retain their stiffness, strength, toughness and dimensional stability at temperature much higher than other aerospace structural materials. Many superalloys are produced using two-phase heat treatment that cause a dispersion of cuboidal gamma particle known as the primary phase with a fine depression between these known as secondary gamma. In order to improve the oxidation resistance of these alloys, aluminum, Cr, B and Y are added. The formation of these superalloys is shown as step-by-step process in a schematic diagram that I have shown below, in which the furnace and a coolant is placed in a same structure. In this furnace, the molten metal is bring down to the coolant step by step. Due to this, the immersion of this molten metal bringing down to the coolant step by step creates a crystal growth on a cold side of a molten metal. Step by step, the crystal elongates along a temperature gradient. Fully solidified, oriented polycrystalline cast is produced at the final. This superalloy can be processed by various methods. First, the casting and forging method, investment casting, direct solidification, powder metallurgy, and also by means of additive manufacturing. This superalloy is mainly three base: nickel base, iron base and cobalt base, and its category is I have shown in the slide. And the application, these superalloys has a vast wide area where the robust and high precise and very high temperature withstanding performance is required, as like the gas turbines, nuclear power plants, engine vanes, automotive engines, aerospace nozzles, medical products and valve seats. In this slide I shown a cut sectional view of a jet engine, in which the rotor is made of ferritic steel and low pressure turbine made of Na based superalloy plus coating, and high pressure is made of a single crystal alloy plus coating, and high pressure compressor is made of austenitic steel, and low pressure compressor made of ferritic steel, and combustor made of Na based superalloy plus coating. Shape memory alloy. Shape memory alloy is a material that undergoes a phase transformation when it experiences a mechanical stress or temperature change. When the condition return to normal, the shape memory alloy remember its original shape and reverts to it. The two crystal structure of SMA material are known as austenite and martensite. Austenite is the SMA structure at high temperature, while martensite is the structure at low temperature. The transformation from austenite to martensite or vice versa is cause of this memory behavior. The common material for SMA includes copper, aluminum, nickel, nickel titanium alloy. The latter is often referred to as nitinol, which refers to its elemental makeup Ni for nickel and Ti for titanium, as well as where it was first developed NOL for Novel Ordnance Laboratory. The changing shape of the shape memory alloy is shown in the figure that I have stated at the right lower corner of your slide, where the original shape is deformed due to force. Whenever the temperature is applied again, it's regain its original. These shape memory alloys are vastly used in aeronautic coupling and solid state actuators, orthodonic arc wires, then endodontic SMA tools, self-expanding stents, SMA bone staple, robotic applications, SMA dampers, eyeglass frames, thin films and MEMS components, etc. Scanning electron microscopy. SM is a type of electron microscope that produce image of sample by scanning the surface with a focused beam of electrons. The full setup of an SEM machine is I have shown in the right side of your slide. Here the electron interacts with atom in the sample, producing various signal that contains information about the surface topography and composition of the sample. The electron beam is scanned in a raster scan pattern, and the position of the beam is combined with intensity of directed signal to produce an image. A schematic working representation of a SEM is shown here, where the electron gun emits the electron beam through an anode. The magnetic lens magnifies those beams and falls on the backscattered electron detector, and the secondary electron detector receives the reflected electron beam from the backscattered electron detector, which is falls over the specimen. So that's how the image is produced. Transmission electron microscopy. Transmission electron microscopy is a microscopy technique in which the beam of electrons is transmitted through a specimen to form an image. It is used to view thin specimen, tissue sections, molecules, etc., through which electron can pass, generating a projection image. The TEM is analogous in many ways to the conventional compound light microscope. The electron microscope transmission has three essential systems: an electron gun, image producing system, and an image recording system. The schematic diagram of an TEM machine is shown here. As like the SEM, the TEM also consists of an electron gun which emits the electron beam through an anode. Here the condenser lens condenses the electron beam, and again it passes over the specimen, which is placed on the between the condenser lens and objective aperture lens. This pass through the tissue or any muscle or any layer of specimen placed between those will penetrate to it, and objective lens capture those image and pass it to the intermittent lens, and also the projector lens, which makes the beam to falls on a fluorescent screen to make an perfect recording of the structure of the specimen placed between the condenser lens and objective aperture lens. Atomic force microscopy. Atomic force microscopy or scanning force microscopy is a very high resolution type of scanning probe microscopy with demonstrated resolution on the order of fraction of nanometers, more than 1000 times better than optical diffraction limit. A schematic representation of an atomic force microscopy is shown in the right side of your slide. Here the probe on the end of the cantilever is scanned over the surface, changing the amount of laser light reflected in the photodiode. The height of cantilever is then adjusted to restore the response signal, resulting in the measure and cantilever displacement tracing the surface. And coming to our final topic, the carbon fiber as our content beyond syllabus. It is a strand of material about 0.0002 to 0.0004 in millimeter in diameter and composed mostly of carbon atoms. The carbon atom bond together in a microscopic crystal that are more or less aligned parallel to long axis of fiber. The crystal alignment makes the fiber incredibly strong for its size. Several thousand carbon fibers are twisted together to form a yarn, which may be used by itself or woven into a fabric. This yarn or fabric is combined with epoxy and woven or molded into shape from various composite materials. Application is mainly in aircraft, spacecraft parts, racing car bodies, golf club shafts, bicycle frames, fishing rods, automobile springs, sailboat masts, and many other components where lightweight and high strengths are. And here I have shown a car, a Koenigsegg, which has 400 different carbon fiber pieces in this car to make this car very lightweight with a higher strength and to achieve a great speed of 434 miles per hour. And its raw material are the 90% of carbon fiber produced by a polyacrylonate and 10% from the rayon or petroleum pitch. And this manufacturing process we have seen about, like it can be wounded or molded or wrapped or drawn into wires to form great structures and complex materials shapes. Some of the process include spinning, stabling, carbonizing, treating the surface, sizing, etc. Thank you students, hope you all understood the topic that we have discussed now. If any doubts, please mail me to my mail ID.